We once thought we understood Pluto, but then came a moment when the truth began to contradict everything we believed we knew. NASA's New Horizons spacecraft flew past Pluto on July 14, 2015. In just a few short hours, the first incoming data challenged every existing model. What would you trust more, the old numbers, or what is about to appear before your eyes? Pluto is not motionless. A world long assumed to be dead revealed ice mountains rising more than 3 kilometers high. A world as cold as -230 degrees Celsius, yet marked by vast icy ranges and a surface so young it cannot be explained under previous understanding. If thermal models cannot explain what is happening, then what else in our understanding is being fundamentally misjudged? Let us explore these mysteries together, because sometimes the greatest discovery is not finding a new world, but realizing that we were wrong about the old one. For decades, Pluto was known as a faint dot on the edge of the solar system. Cold, dark, a world without an atmosphere, without geology, without energy. At an average distance of nearly 39 AU. With surface temperatures around -230 degrees Celsius and a mass just 0.2% that of Earth. How could anything there still be considered alive? Yet, science shattered those assumptions in just a few hours during New Horizons flyby. When the first data arrived, what emerged was not a silent ball of ice. On the hemisphere facing away from Charon, a massive heart-shaped structure appeared, brighter than the surrounding terrain and almost completely free of impact craters. Scientists named it Tomball Regio, stretching roughly 745 by 1,240 miles. Comparable in size to the entire country of France. But the real shock lay in its age. Statistical models suggest the surface of this region may be younger than 10 million years, with some areas only a few million years old. This discovery shattered the core belief that Pluto had long since cooled into complete geological dormancy. If the surface is being continuously renewed, then some mechanism must still be at work. Not impacts, not wind or liquid water, but a form of internal activity, slow, cold, yet persistent. Gravitational data and surface geometry reveal that this heart-shaped region is a positive mass anomaly. It behaves like a heavy weight, pulling Pluto's icy crust to face Charon. This unusual form of tidal locking suggests that beneath Tomball Regio may lie a thick, dense layer of material. One hypothesis has risen to the forefront, a subsurface ocean that once existed, or may still exist beneath the ice. If Pluto's rocky core makes up roughly 65 to 70% of its total mass, The radioactive decay of uranium, thorium, and potassium could generate internal heat lasting billions of years. Compounds such as ammonia could further lower the freezing point of water to below -100 degrees Celsius. Tumbal Regio thus stands as direct visual evidence that Pluto is not inert. It simply operates on a rhythm entirely different from Earth's. When we look into the heart of Pluto, we are forced to ask a fundamental question. If a world this small, this distant, and this cold can still retain energy and renew its surface, then how many other dead worlds out there are actually alive in ways we do not yet understand? And once that door opens, we begin to recognize the next mistake we've been making all along. On Earth, ice is a symbol of stillness, rigid, brittle, cold, and motionless. But on Pluto, ice does not merely exist, it moves. Pluto's average surface temperature hovers around -230 degrees Celsius. Under those conditions, water freezes into rock-hard ice, but Pluto is not composed primarily of water. Its surface is dominated by three volatile compounds: nitrogen, carbon monoxide, and methane. At such extreme cold, these substances also freeze into solid form. Yet their viscosity is far lower than that of water ice. Mechanically, they behave more like a dense plastic capable of deforming, flowing, and reorganizing under Pluto's weak gravity. Imagine standing on a plateau of nitrogen ice. There is no cracking sound, no rapid motion. Yet beneath your feet, millimeter by millimeter, the surface is shifting. Layer upon layer of ice flowing at a pace of only a few centimeters per year. Too slow for any living organism to perceive, but fast enough to completely renew a plain spanning millions of square kilometers over a few million years. At the center of this motion lies Sputnik Planitia, a vast nitrogen ice plain embedded within Pluto's iconic heart. When high-resolution images from New Horizons were analyzed, scientists noticed a striking geometric pattern. Enormous polygons, each measuring roughly 12 to 18 miles across, covering the entire surface. These were not random fractures. When material at the base becomes warmer and less dense, it rises. As it reaches higher levels, it cools, grows denser, and sinks. Thermal models show that a temperature difference of just a few Kelvin between the bottom and top of an ice layer several kilometers thick is enough to trigger convection. The result is a continuously self-renewing surface where ice rises and sinks like a colossal viscous fluid. What makes this truly astonishing is that Pluto lacks strong tidal forces like those acting on Europa or Enceladus. Only faint internal heat left over from Pluto's formation, combined with the unique physical properties of nitrogen, is enough to drive this process. When we look at Sputnik Planitia, we are not simply seeing ice in motion. Each polygon is a convection cell, persisting for hundreds of thousands of years before being reshaped. And once we understand that ice can flow, that motion does not require warmth. If Pluto is large enough to sustain convective ice currents, if it is complex enough to continually renew its surface, then have we misunderstood its size and internal structure from the very beginning? The answer lies in the next mistake, one rooted not in ice, but in light. In planetary science, size is often used to infer mass, density, and internal structure, and from there to decide whether a world is still alive or long since dead. With Pluto, that chain of reasoning was flawed from the very beginning. For most of the 20th century, Pluto was nothing more than a faint point of light on the distant edge of the solar system. The turning point came in 2015, when New Horizons flew past Pluto at a distance of just over 12,500 kilometers. For the first time, humanity was no longer forced to guess from dim reflected light. We could measure directly. Pluto's diameter was determined to be about 2,377 kilometers, significantly larger than many earlier estimates. When this revised size was combined with Pluto's known mass, derived from Charon's orbit, its average density was calculated to be around 1.85 to 1.88 grams per cubic centimeter. This implied a rocky core, making up roughly 65 to 70% of Pluto's mass, wrapped in an ice shell hundreds of kilometers thick. The mistake was not in the data, but in the conclusion that Pluto could not sustain long-term geological activity. Once its true size was revealed, a larger rocky core means the ability to retain heat far longer, not for hundreds of millions of years, but potentially for billions. On that timescale, even the slowest processes can reshape a surface, reorganize ice layers, and sustain subtle internal mechanisms. More striking still, the thick ice shell above the core acts as insulation, turning Pluto into a slow but stable thermal system, one that does not require explosive energy, only time. Here, a familiar human bias becomes clear. We tend to underestimate things that are small and distant. In our intuition, only large planets like Earth or Mars seem worthy of internal power. When size is finally placed in its proper context, Pluto stops being a strange exception. It becomes a textbook example of a methodological error, judging internal activity based on impression rather than structure. And once Pluto's true structure comes into focus, a deeper question emerges. If its rocky core is large enough, if its internal heat is durable enough, then where has that energy gone? Has it merely melted ice, or has it been quietly driving something far more powerful, far deeper, and underestimated for decades? On Earth, internal heat is expressed through erupting volcanoes, glowing red lava, and violent earthquakes. But on Pluto, heat does not erupt violently. It accumulates and is released through pathways we once never considered geological. The clearest evidence appears in the form of a massive, unusual structure standing alone on the surface, Rethinking. With a diameter of roughly 150 kilometers and a height of about 4 kilometers, Rethinking resembles no impact mountain ever seen in the solar system. It lacks the sharp circular rim of an asteroid crater. Instead, it has a large summit depression, gentle slopes, and signs that material once welled up from the interior. This is cryovolcanism, ice volcanism rather than molten lava, and Rethinking is believed to have erupted a mixture of water and ammonia. Under normal conditions on Pluto, water would freeze as hard as granite. But when ammonia dissolves in water, it fundamentally changes the physics, lowering the freezing point to below -100 degrees Celsius, and even lower depending on concentration. This opens an extraordinarily important thermodynamic window. Liquid water could persist inside Pluto far longer than scientists once believed. The heat driving this process does not come from tidal forces, as it does on Europa or Enceladus. It comes from within, specifically the radioactive decay of uranium, thorium, and potassium in the rocky core. When combined with the thick ice shell above, this internal heat does not escape easily. It is trapped, stored, and gradually softens the internal structure. The result is not frequent, violent eruptions, but rare episodes of icy outflows separated by tens or even hundreds of millions of years. It is here that the hypothesis of a subsurface ocean beneath Pluto's surface becomes serious. Structural models suggest that if the ice layer is thick enough, if the rocky core is warm enough, and if ammonia is present at moderate concentrations, then a cold, salty ocean trapped between rock and ice could indeed exist, even persisting to the present day, or freezing only in the recent past. This completely changes how we view Pluto. From this perspective, Reitman's is fossil evidence that Pluto once and may still release energy from within. If internal energy is sufficient to drive ice to the surface and sustain complex structures below, then could it also be enough to accomplish what once seemed impossible, retaining an atmosphere? The answer leads us directly to the next mistake, the one involving the most fragile, yet most misunderstood, feature surrounding Pluto, its atmosphere. When New Horizons swept past Pluto in 2015, one of the most puzzling discoveries did not come from the surface, but from what surrounded it. Spectral measurements and stellar occultation experiments revealed that Pluto possesses a real atmosphere, thin, fragile, yet far from insignificant. Surface pressure was measured at around 10 microbars. That value is only about 1/100,000th of Earth's atmospheric pressure. Yet it is far higher than what had ever been predicted for a body as small as Pluto. Its atmosphere is composed primarily of nitrogen, with smaller amounts of methane and carbon monoxide. The presence of these light molecules overturned earlier models. As Pluto moves closer to the Sun along its elongated 248 two-year orbit, nitrogen ice on the surface begins to sublimate, releasing gas into the surrounding space. During certain phases, the entire atmosphere may nearly collapse, only to reform again as conditions change. New Horizons also detected a phenomenon that forced scientists to pause and rethink everything from the ground up. Faint, layered hazes stacked within Pluto's atmosphere, extending hundreds of kilometers upward. They are not thick, not dark, but they are enough to demonstrate that atmospheric chemistry is still active. Under the influence of ultraviolet radiation from the sun, methane molecules break apart and recombine into more complex organic compounds, gradually forming suspended haze particles. Pluto demonstrates that even a small world can sustain an atmosphere, as long as physical processes are arranged in the right way. And it is precisely this fragility that makes Pluto extraordinary. Its atmosphere exists on a razor's edge between presence and disappearance, between freezing and sublimation. A slight change in solar energy can alter its entire state. This turns Pluto into a natural laboratory for extreme climates. Climate systems unlike anything found on the familiar planets of our solar system. But the story does not end there. Those thin haze layers are not merely passive byproducts of chemistry. They are interacting with energy in ways older models cannot explain. They absorb sunlight, emit heat, and may be regulating Pluto's climate through an entirely new mechanism. Because when the James Webb Space Telescope looks at Pluto, it does not see just an atmosphere. It sees a climate system without precedent. With its ability to observe in the mid and far infrared, JWST looked directly into the region where older models failed, and the results were genuinely shocking. Instead of warming Pluto's atmosphere, its haze layers are actually cooling it. Haze particles absorb solar energy during the day, but rather than trapping heat, they radiate it away very efficiently in the infrared at night. This effect causes energy to be rapidly dispersed into space, making haze the primary thermostat of Pluto's entire atmosphere. This behavior has never been observed on any other planet. On Earth, greenhouse gases retain heat. On Venus, thick clouds lock energy in, producing a runaway greenhouse effect. On Titan, haze warms the upper atmosphere while cooling the surface. But on Pluto, haze reverses the role. It becomes a heat emitter, not an insulating blanket. The mechanism behind this phenomenon lies in the nature of the haze particles themselves. They are extremely small, structurally complex, and highly interactive with infrared radiation. Pluto's climate is not governed by gases, but by particles, not by mass, but by microstructure. A small world operates its climate system using components once considered secondary. If haze controls the energy balance, then Pluto's climate becomes extraordinarily sensitive. A slight change in methane abundance, photochemical rates, or orbital illumination cycles could reshape the entire thermal structure. Pluto does not have a stable climate in the familiar sense. It has a flexible, oscillating climate, constantly adjusting. And that is precisely what makes Pluto unique. No rocky planet in the solar system operates this way. No known icy moon possesses a haze system that controls global temperature. Pluto stands alone, like a natural experiment where climate rules are rewritten from first principles. Pluto shows that when conditions are different enough, physics finds a different path. From a thin, seemingly passive atmosphere, Pluto becomes an active climate system, one in which inert organic particles play a central role in regulating energy. And if these haze particles are the products of organic reactions spanning billions of years, If Pluto's surface and atmosphere are continuously exchanging material, then is this world merely a climate laboratory? Or could it also be a laboratory for non-traditional forms of biology? The turning point begins with a discovery that seems small but carries profound implications: traces of ammonia on Pluto's surface. Spectral analysis reveals clear absorption features at wavelengths around 1.65 and 2.2 micrometers, chemical fingerprints that are difficult to mistake. Ammonia is not a stable compound on a surface exposed to constant radiation. It is easily broken down by ultraviolet light and high-energy particles. Imaging data and topographic maps show that the presence of NH3 is strongly correlated with tectonic fracture zones, especially the region known as Virgil Fosse. These are not random cracks caused by impacts. They are extensional structures, suggesting that Pluto's icy crust once or may still be under stress from internal forces. This opens an entirely new way of thinking. If beneath Pluto's ice shell there once existed, or still exist, pockets of liquid water rich in ammonia, maintained by weak but persistent internal heat, then we are looking at a chemically stable environment unlike anything on Earth. No photosynthesis is required, no carbon cycle as we understand it. Only chemical energy, a liquid solvent, and time. Here, we enter the realm of non-traditional biology. Systems that could sustain themselves, self-organize, and evolve in conditions without light, without oxygen, and without familiar temperatures. A form of life that, if it exists, may never leave obvious signatures like green leaves or oxygen in an atmosphere. Pluto, therefore, becomes a candidate for expanding our very definition of life. What is striking is that the conditions Pluto possesses are not unique. Icy worlds at the edge of the solar system, icy moons, and even many cold exoplanets orbiting red dwarf stars may share similar traits. Weak internal energy, nitrogen, rich chemistry, and non-pure water liquid solvents. If Pluto, a world once dismissed as completely dead, can support long-lasting complex chemistry, then excluding countless other worlds simply because they do not resemble Earth begins to look increasingly careless. From this perspective, Pluto acts like a mirror. It reflects not the limits of nature, but the limits of our scientific imagination. From the moment it was proposed, New Horizons was considered an insane mission. Launched in 2006, the spacecraft blasted out of the solar system at record speed, crossed Mars's orbit in just a few months, and relied on a single gravity assist from Jupiter to gain velocity. There was no backup plan for Pluto. There was no second attempt option. Nearly a century of scientific debate about an entire world was compressed into just a few hours of close approach. The mission's cost, about $720 million US, was modest compared to many other space programs, but the risk was enormous. Any failure in power, orientation, or data storage could have turned New Horizons into a silent bullet, flying past its target without leaving a single message for humanity. On the historic day New Horizons flew past Pluto, the spacecraft did not transmit data directly back to Earth. All of its energy was devoted to observing, imaging, and measuring. The data were stored on board, and only later, over many months, were they slowly transmitted back, packet by packet, at speeds that felt almost unacceptable in the internet age. Every image and every spectrum arrived with tension attached, because if the data were corrupted, there would be no backup copy. When the data finally began to arrive, the impact of the mission extended far beyond Pluto. It shook the way we evaluate distant worlds. In hindsight, New Horizons was not just a Pluto probe. It was a test of the scientific method itself. Are we willing to send a messenger that far simply to test whether we might be wrong? After Pluto, New Horizons continued deep into the Kuiper Belt, exploring Arrokoth, a pristine relic from the dawn of the solar system. This reinforced a key message. The mission was not meant to close the story of Pluto, but to expand our understanding of how worlds form and evolve in extreme cold. Perhaps the greatest legacy of New Horizons lies not in numbers or images, but in a more subtle shift. It taught us greater humility in the face of the universe. It showed that what we consider distant and small can harbor systems of complexity far beyond our expectations. And that untested confidence may be science's greatest risk. When New Horizons left Pluto behind, it did not carry final answers with it. It carried proof that the original question itself was wrong. From that moment on, the entire story had to be retold, not to highlight failure, but to understand why we were bound to be wrong when observing from so far away. All that remains now is to connect the pieces, from data to assumptions to the limits of human perception. And that is where the story closes in Part 11, Conclusion, where being wrong is no longer something to be ashamed of, but an inevitable part of the journey to understand the universe. Early inaccurate conclusions about Pluto were not failures of scientific thinking, but evidence of the unavoidable limits of observational technology when facing a universe of immense scale. For decades, When Pluto existed only as a few faint pixels at the edge of the solar system, theoretical models unintentionally simplified the true nature of a world that was, in fact, dynamically active. The arrival of the New Horizons mission forced us to redefine what it means for distant celestial bodies to be alive. A dwarf planet, once considered a dead object, turned out to possess a changing atmosphere and remarkably youthful geological activity. This demonstrates that the universe is always richer than any scenario humans can imagine. In the end, Pluto is not only an exploration target, but also a lesson in humility. It reminds us that science is not a collection of immutable truths, but a continuous journey of correction in pursuit of truth. In infinite space, the greatest barrier to knowledge is not a lack of data, but the illusion that we already know enough, an illusion that lulls us into complacency and erodes curiosity, the only force capable of carrying humanity across billions of kilometers to touch the final frontier. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.